Hello, this lecture is about the spatial discretization of a continuous world so that we can actually solve our field applications in a numerical model. As we discussed before in this course, we will use continuum mechanics. And if we look around us, the world is continuous. There is no intersections. However, numerically, I need to discretize the space so that I can solve it. And you might remember this scenario. I used this figure earlier of the catchment model. We have a river going through different kind of maybe soils or sand types. And now if you want to simulate something like this numerically, you need to split it up into discrete cells, which are indicated here by those gray lines. And here I didn't do it very carefully. You see that the sizes of these cells are different, have different sizes. The spacing is not correct. But that we will discuss those effects later on. But for here, it's not for you. The understanding means for each of those cells, we would calculate a value, right? For example, of our pressure head, right? You calculate the values of the variables of the governing equations you are solving. That means this kind of grid, it would be very coarse. So only for each of those cells, I would get one value. Means now when I have here the river and some soil or here, that means I would just get one information for the cell, independent of what is physically represented. So it's a mean value. I could resolve that, for example, with a finer resolution. Means smaller cells, more of those cells. And this, of course, would increase, let's say in some way, the quality. I'm being careful with this word, but for now, for the introduction, you might know, have an understanding of it, right? I would have higher spatial resolution, maybe being more accurate. Also, accuracy is something we will talk about within this course. Be careful with using this word. But of course, when I have more cells, means I have to do more computations, because for each cell I have to solve my differential equation. Means having more cell, I have more computational load. This would, on the same computer, increase my workload. Right? But this is the idea. So we have a continuous world, and we need some kind of discretization. And this whole lecture is about the discretization techniques you can use to apply such kind of application in a numerical model. So first things first, getting some wording done. So what I used on the previous slide was quadrilateral elements, rectangular elements, right? So we call that one an element. So what is inside our rectangular box? That's the element. Each element has a center. You can also, it's a different perspective. You're not talking about elements, but about nodes. So for example, this one would be a node. Or another very popular shape, if it's not rectangular, it's triangular. Right now we would also call here something like this, we would call an element. On all those cross points, we would call nodes, right? And in triangular meshes, it's seldomly that you talk about the center of an element, but also this would be fine. Okay, and there are much more types of elements. So pretty much any geometrical figure you could think of could be used to discretize that space. But those two are the most common ones, and we will discuss a bit later what is the benefits and drawbacks of each one. Because when I have rectangular or quadrilateral meshes, I'm often talking about structure meshes. Structure just simply means, well, there's a structure, there's a regular rule behind it, how this mesh was generated. And that means when I know where I am, I directly know who my neighbors are, right? So then go for such a Cartesian grid, which means each cell has the similar size. It doesn't mean that X and Y direction of each cell, so the length and width of each element are similar, but it means all elements have the same length or the same width. So when we look at this one, I'm this cell, I directly know who my neighbors are. This follows simple mathematical rules, right? Also, those kind of cells if it's 1D, 2D, or 3D, it doesn't matter. They translate to an array of a similar dimension, right? So if this is my solution field, and for example, I calculate pressure head, so for each of those elements, I want to store the pressure head value. I can store it in a 2D array, so in a matrix, pretty much, and I directly know, so my neighbors in the matrix are my physical neighbors on the grid. This is very good. That's very easy for me because I have to store very little information in my memory of my computer, and the access is done very, very quickly. Usually, also structured meshes have a very good convergence. We will talk about this in one of the following courses, which simply means that the solution usually is quite smooth solvable, right? The Cartesian grid is, I said, the simple one. Doesn't need to be that simple, right? We can have different element sizes that still I can store this in a 2D array, right? I would still need additional information knowing the width and length of each element, but that's okay. I can do that, right? Or you can also do something like this, like a curvilinear grid. Still, my neighbors are well defined for every cell. On the other hand, for unstructured meshes, I don't have this regularity, right? But I'm gaining something. I can rebuild complex geometries, right? So even when we look here at a circle, I can't reproduce a circle with quadrilateral elements or with any kind of structured mesh. It's getting, well, with a curvilinear mesh I could, but it's getting very, very complicated. And this is, well, a classical triangular mesh. Not a very good one, as we will discuss in the next slides, but still it is. But you will notice is that I cannot really directly interfere who my neighbors are, right? I could also connect the nodes differently, come up with a different mesh. Okay, so what you do is you store the coordinates of its elements. You store connectivity, so which element is connected with which. So that means I have more memory demands for my computer, which I need to solve, right? And so triangles are the most classical one because you can represent a lot of complex geometries with triangles. If you go to a 3D space, 3D simulation, yeah, you would go for tetrahedral geometries. But the triangulars in a 2D are the most common ones, right? So a lot, if you go on the net and you Google for unstructured meshes or find element, or we'll see in a second, you will usually get these kind of triangular meshes because they are so great for complex geometries. What also you can do is here, you can easily refine it. So you imagine if you have the structured grid and you want to introduce additional points, this is difficult because you always have to remain the structure. So you can't add a single point, but you can add a lot of more points than in the same way. Here in unstructured meshes, because I have to store everything explicitly anyway, I could just say, okay, I want to have an additional node point here, and then just I have to do my meshing new. I have to reconnecting the points in a different way, but this is quite flexible, quite easy. How do you generate those kind of unstructured meshes? The usually way for the triangular is Delaunay triangulation, which pretty means you're connecting the points in a way so that no other points are within a circumscribed circle, right? So you have this point, you're drawing a circle, and all the points that are lying within this circle are connected to me, all right? If I go further out, like up here, right, then I wouldn't connect it anymore because I can't connect it to this one anymore if I connect those ones. The Voronoi tessellation is more for a different kind of technique, we'll discuss in a second. What you do here is like it's an organic growth. So from each point, you are growing your volume until you come in touch with the volume or the area of another point, and then you stop. This way means each line is closest to the 2 points and further away to all other points. right? So you can see this one here, those points are really close, so it means when they are growing, they're very much coming in contact, they stop. Here there is a very big difference, so they're growing radially, and as soon as you circumstance sources make it that you touch the other area or volume, you stop, and then you get the borderlines. So I really recommend you watch some YouTube videos or so on that. It's very nice looking at how these generates, and the process is much simpler to understand. But the principle again is each line is closer to the two centers than to any other center. So how do you separate a good or bad mesh? I already showed you the circle mesh and said it's not a good one. Why isn't it a good one? Because there are aspects you want to consider in a model. You want it that it has no sharp contrasts in element size, especially not in neighboring elements. So what you have is that things, for example, with depth, you use larger meshes. That's okay, but you have a smooth transition. You're not doing something like here having comparably small triangulars just next to big ones. That's a bad idea. So this kind of meshes with the green one, right? It's much better because all elements have almost similar size. Here I have a strong contrast in element size. That's something that's not good. Also, what you want to have is an aspect ratio, so a ratio of the length and width of each body. Then this is close to 1, right? So having all lengths equal. And you want to avoid like sharp angles and stuff like this, which comes with a bad aspect ratio. But right, also this one, it's a very, very long one. This is not so good, right? And here you see for the, I mean, that's something that also applies to the structured meshes, right? You don't want to have like your spatial resolution X and Y to diverge so much, right? You want to have it in a good aspect ratio. So this is coming back to this example I showed. Why is it in bad example? Because if you compare, for example, the meshes, the triangulars I marked here in blue, we have a big one, we have a small one, very close to each other, right? And we have here elements with a very, very sharp angle. This is not a good mesh, right? It was just drawn by me by hand, and you see that that's not good. But however, don't worry, you don't have to do this by your hand. Most software you will use for groundwater modeling comes with that, right? So you just say generate mesh, and it will generate you a mesh. And it will do this in triangular if it uses finite elements, or in kind of any structured mesh if you use another different method, right? But still, sometimes the algorithm is not doing very good work, and you wanted to refine the mesh, and then you should know how it was done. Also, like often you will find in reports, documentations that people show you the mesh you're using to show you that they know what they're doing and that that's a proper mesh, and you're not introducing errors because of a bad mesh. Because what you want to do is you want to have an convergent, good, high accuracy simulation result. And if you have a bad mesh, your solution might not converge, or other kind of errors may occur. Your solution gets inaccurate, stuff like this, all depending on the spatial discretization. So having a good spatial discretization is an important starting point. You can do a lot of things wrong right from the beginning. I always said is what happens you're doing a mesh and you notice, well, okay, there is an area where there's a lot of action. I want to have this in higher resolution. I want to understand better this specific part, what I can do. And this is where these strengths of these unstructured meshes, you can very easily increase accuracy at specific points. You can do this on structured meshes as well. There is no limit on that. It's just maybe not as straightforward as it is for unstructured meshes. Always remember, more points means more computational costs. This is especially true if you do this well, during runtime, or if you're adding more nodes during into an existing grid, because as I said before, you will need to change the meshing, so you need to reconnect your element nodes differently. Then there is a specific term which is called adaptive mesh refinement, which simply means that the algorithm itself gets to know, oh, okay, there here now, for example, I have a steep contrast. I tried to highlight this here. So imagine this is some aquifer and there is some solute which is transported from left to right. And there is, there's a steep gradient. So there is a lot of action going on right now. So you might, want to resolve this one a bit finer, because we will discuss in the future of this course, steep gradients are always difficult numerically. So you want to resolve it quite finely. And adaptive mesh refinement means the algorithm itself knows, okay, here's nothing happening. I can have big cells over here. Nothing is happening here. I can have big cells over here. But this is the area where all the action goes. So I will have a lot of fine meshes here. And then you keep running with the simulation. And at some point your front is moving, and now your tracer front is over here, your steep gradient is over here. And now you want to have this region highly discretized. And where we were previously, so over here, now there is no action. So there's no reason to have a fine mesh over here. All right. So this is what's called adaptive mesh refinement. This is a very complex process. It's high computational demands. And I mean, expect no one to develop something like this, but if you find software that's able to do this, or people tell you that they did this, then you understand what they're doing, and you understand. Well, it tells you a lot about the quality of the work they are doing. There is a nice YouTube video online. I recommend checking it out, where you see this mesh refinement in reality, in application, in comparison to how the results look like with mesh refinement and without mesh refinement. And this is very impressive. I really recommend to check it out. So what we need to do is, now we discretized our domain in some way, but we still need to put points of the physics to these points, right? And there are a lot of methods. There are also something that is called meshless methods. So which method that's solving numerically without a mesh. These are advanced topics you will hardly find in groundwater modeling. So I will just go here with the 3 classics, which I know are employed in groundwater modeling. So the finite differences method is the oldest method of all of those. It's very popular, and it's conceptually the most simple method. So I will talk a bit more about finite differences than about the others, because we need very little mathematical overhead for the finite differences. And well, the principles are still quite comparable between the different methods. So I hope you understand a bit how numerics works based on the example of finite differences. The basics of finite differences is it's based on structured meshes, right? So it has this regularity to it. It has difficulties with complex geometries. It's not really made for that. It's still possible, but it needs extension to the original theory. And the concept here is we have discrete points, and we look at the relationship between these discrete points, right? So thinking about this contaminant moving from left to right from the previous point. So you say, well, okay, if I have on the left side high concentration than at my point, and then even less on the right side of myself, well, and the water is flowing from left to right, so that means the concentration is increasing from left to right as well, increasing concentration. So how much it increases depends on the difference between those different positions. The finite element, on the other hand, is using unstructured meshes, and here it's based on the integration of elements. We'll talk about this a bit more in the future, in just a couple seconds. But the idea here really is you're connecting elements or nodes, or you're connecting nodes using, for example, triangular elements, and then you're integrating over this triangular based on the values on the nodes. Finite elements nowadays is probably the most common method, especially engineering applications, because its benefits in terms of complex geometries. It is a bit more higher computationally demanding than finite differences, but for the users, so for you, the programmers have already done all the work. So for you, it doesn't make much difference on the usage, and you're just benefiting from the usage of unstructured meshes on complex geometries. The third method, finite volumes, is especially common in fluid dynamics. So it is, well, also a good point to use in groundwater hydraulics. You can use finite volumes on structured and unstructured meshes. This is no problem. And as the name already says, it's based on the integration over volumes and fluxes across those surfaces. And here you already see this connection to what is said, the conservation of mass in the groundwater governing equations. And so this is really based on this, and it's very conservative and very close to the mathematical concept. So this is why it's especially useful in fluid dynamics. So the finite differences, as I said, it's the most simple method, and because it's based on the Taylor series expansion, right? So the idea is in discrete points, the derivative of a function with space, you could approximate by the difference between the neighboring points divided by the distance between those points, right? So we look at the point here, function e and j, so these sub-indices make for x and y direction, right? So now we are in a discontinuous space, so discrete elements, discrete points. So we're not talking about like meters in x and y direction, but we're talking about which kind of element it is. So we're numbering it. And it says, well, the derivation or the change at this point in x direction, I can approximate by taking the value here, taking the value here, building the difference from it, and divide it by twice the grid spacing. So dx is the grid spacing. As you know, Taylor series expansion, that means there are then higher order terms which are neglected. All right, and then you can do the same thing in y direction. So using this method is something that is called centered in space, because I'm calculating in the center, I'm calculating my value based on the neighboring points. But no one says you have to use those 2 points. You can use more points on the left and right. You can just use, for example, those 2 points. Bunch of things you can do. All of that is possible. There are names for this. These are called schemes or stencils, right? Different kind of combination of points. The accuracy of your method, the stability of the method will vary which kind of stencil you're using. Your application, so your physics, will define what kind of stencil to use. However, again, don't worry about it. As a user using some kind of commercial software, all this is already done, right? So for groundwater hydraulics, for this kind of partial differential equation, it is known what kind of stencil is good, which gives you good accuracy, and this one is applied by the programmer to solve the differential equation. All right, but this is for you to know what's happening under the hood. Right, so giving you just an idea, why I said it was centered in space, you can do the same, for example, for forward in space, saying, well, I'm just taking this point and building the difference between those two and just divide it by the grid spacing dx, because now I have neighboring points, right? Or you can do this backwards as well. And the reason why I explain this one here so much in detail is because next, when we in the next lecture, when we talk about time evolution and how we simulate progress in time for transient problems, those are similar methods, because in time you're always applying finite differences, and then you will remember those kind of equations, and it's nice to remember it here on a spatial scale. Of course, as I said, you don't need just to use the neighboring points. You can also use further away points, right? So here, for the similar scheme as I said, centered in space, we're now not just involving the next neighboring points, which would be those two, but it will also be involving points which are further away. So we would involve this point and the point which is not shown over here. So this is all possible, and you can have not just first order derivatives, but also second or third order derivatives. So this is all tabulated, all the coefficients are known. This is in the books. So there's nothing to learn, it's just for you to understand how those kind of derivatives work. right? And the literature I'm recommending here is the Spatial, so the numerical recipes. It really is what the name says. It's a cookbook. There are recipes for all the different kind of differential equations, how to implement it, what method to use for what kind of scenario, right? I also recommend the book of Taras Geyer from 2009, Introduction to Numerical Geodynamic Modeling. This is, as you know, not so much related to groundwater hydraulics because it's focusing more on geodynamic problems, but based on MATLAB code, it introduces you to a lot of the finite differences vocabulary and also towards advanced methods, which I will not discuss here. For example, Marcus and Seld or Stetched Grid. So there is additions to this classical, very bare-bone finite differences I introduced so far. You can add things on, make it more complex, but also increasing different aspects and try to get more out of the finite differences. Because, for example, then in terms of advection or stress calculations, where you would use those kind of advanced methods, right? And you can also use those kind of advanced techniques to overcome the limitations on geometry. So I said finite differences are operating on regular grids, but you could overcome this with some additional efforts, right? That it's used so much is simply because it's fast, it's flexible, and it's easy. Also for developers as well as for the users, right? And there is software packages for groundwater modeling based on finite differences out there on the market. So the other methods are mathematically more complex. I won't introduce it here in detail because this course is not about writing your own software, but about using software that does a simulation for you in a meaningful way. And as I said before, the finite element method is based on an integral approach. So finite differences is based on the approximation of the difference between points. Here we are integrating over an element, so over an area. And the question is, how are you integrating? So that means if we just have a simple 1D problem, we have a node here, we have a node here, we have a node here. So we have discrete points again. And now you want to calculate the area, or you want to calculate your variable over the area. So within your element, which in a 1D case would just simply be a line. And that means you need to weight the information from one node to another. And again, similar to finite differences, there are a great number of methods on how to do this. The most usual one is the so-called Galerkin technique, which means you multiply your value with a weighting function. Of course, if I'm at my node position xi, this information in this node will be 100% my value at this point. But the further I go away, this weighting function the influence of this information will decrease and the information of the neighboring point will increase. So if I would draw the weighting function for the value xi plus 1, it would look like this. Or for xi minus 1, it would look like this. So you see in the sum, both end up always at 1. But as further away you are from my node, as less important its information will become. Right? So this comes up that the apparent value of my function in a two-space one would be the sum of all my involved nodes. Depends on how many nodes you are involving, usually the ones that build your element, right? And you multiply that one with the weighting functions and add it up, and then you integrate over the element. This is what finite elements technique is based on. So you approximate the function with a set of basis function. As I said, there are different kind of basis function. The Galerkin method is just one, the most common one, but there are a lot of other things. The coefficients which you then multiply your node value with depend on the value of those basis function. And the final solution is obtained by solving a linear system of equations. This is numerically a standard procedure, but it is kind of costly in terms of calculation efforts. The really good thing is because it's operating on unstructured meshes, can be applied to any kind of geometry, and elements can be placed anywhere, so you can have a variable mesh density. As I said, if you do simulations with depth, you usually have a higher resolution on the top because there we have more information. As deeper you go, as more unsecure our information becomes, so you make a less dense grid there. Or if you have boreholes, you usually discretize with a high resolution around the boreholes, and as further away you go, as larger your elements become. Right. And as I said, because unstructured meshes, you can add or remove nodes, you can deform them even. So there are a lot of possibilities, and that's why it's so often applied in numerical simulations, especially engineering applications. Finite volumes, as I said, are especially helpful for fluid dynamics because they are based on the Gauss theorem. So I don't want to go into detail here, but what it's expressing is we have a lot of divergences. So the multiplication of an nabla operator with a vector field, and we integrate this one over volume. But the Gauss theorem, so it's a general mathematical law which is proven correct, tells me I can convert this one over the closed integral. So that's why there is this little circle in the integral. Closed integral about this same vector field multiplied with the normal vector on the boundaries of this volume. Right. So instead of integrating over the divergence of a vector field over volume, I can integrate the vector field or the flux of the vector field across its surface. And this is, for fluid dynamics, we have some mass moving from one volume to another, right? This is very close to what's actually happening in our mathematical concept. And that's why we call it mass conservative, because there can't be mass lost. Because everything what leaves one cell is automatically entering the neighboring cell. And by other methods, this is not often given. So there can be problems. That's what we discuss in a future lecture. Instability, inaccuracies, because they're not mass conserving. But finite volumes do this, and this is one of the strong benefits of it. Right? And this is where, for example, you would come in with the calculation of Voronoi cells, because well, the whole area needs to be covered with cells. And if you use unstructured meshes, you would use Voronoi cells, for example. That's why I introduced it at the beginning. Right, but you could also use structured meshes without any problem. So what I want you to learn from today is what is a good mesh and what is meant by the term mesh refinement. Yeah, I want you to know the different kind of meshes, including the pros and cons. We introduced two methods to come up with unstructured meshes, so Delaunay triangulation, Voronoi cells. And I want you to know the terms, finite differences, finite elements, finite volumes, and know what the benefits is, what the drawbacks are, and how to use it. And especially just simply know the term that when someone says, well, I did a finite element simulation, that you know what he means or she means when they say this kind of term. Thank you very much.